Hi everyone, this is Professor M. Science, and today I want to talk about the occupation number representation in another one of our videos on rigorous quantum mechanics. We already know that bosons are described by totally symmetric states, while fermions are described by totally antisymmetric states. When working in the position representation, the states are represented by permanence in the case of bosons and Slater determinants in the case of fermions. If these names sound a bit strange, make sure you watch the video on the symmetrization postulate before moving on. These representations are very useful, and they feature in techniques from quantum chemistry all the way to material science and condensed matter physics, for example in the shape of Kohn-Sham density functional theory. What we'll see today is that this formulation has some redundancy built in it, and as such is not ideal for some applications. What we'll see is that the occupation number representation provides an alternative compact formulation to describe systems of identical quantum particles, and it forms the basis of something called second quantization, which is an extremely powerful tool to do quantum mechanics. So let's go. The basic idea behind the occupation number representation is very straightforward, so before we delve into the maths, I want to start by providing a simple intuitive picture. Imagine that we represent a system of identical particles by a collection of identical balls, and we pick a 6-ball system. Also imagine we have a shelf, and we label the levels as 1, 2, 3, and 4. An example of a state of our system is given by 2 balls being in shelf 1, 1 ball in shelf 2, 3 balls in shelf 3, and no balls in shelf 4. As these balls are identical, I can exchange any 2 balls like this, and I will end up with the same situation. So how can we describe these states? One way would be to assign a number, 1 to 6, to each of these balls, and then say that level 1 contains balls 1 and 2, level 2 contains ball 3, level 3 contains balls 4, 5, and 6, and level 4 contains no balls. However, we said earlier that exchanging these 2 balls would not make a difference because the balls are identical, so what does that mean? In this description, having exchanged the balls takes me to the following situation. Level 1 now contains balls 3 and 2, level 2 now contains ball 1, level 3 still contains balls 4, 5, and 6, and level 4 still contains no balls. This now looks like a different configuration of the system in levels 1 and 2, but we know that in reality the situation is the same because the balls are identical and the labels are artificial. So this description has some redundancy built in, and labeling balls is clearly not a very good way of representing this system of identical balls. In quantum systems of identical particles, if you check the video on the symmetrization postulate, you will see that we have so far built our state in a very similar fashion. We have constructed states by first building an n-particle state in which we labeled individual particles, and then applied a symmetrizer or antisymmetrizer to construct all possible permutations of these states, ending up with expressions containing n factorial terms, which as we will see later in this video also lead to a lot of redundancy. Both examples suggest that there should be an easier way of describing these systems of identical balls or identical particles that captures the basic idea that nothing changes when 2 identical balls or 2 identical particles are exchanged. To see how this works, in the case of identical balls, let's define the shelf again, and place the balls again. Consider a new description in which we only specify how many balls are in each level, irrespective of which ball is which, so that in level 1 we have 2 balls, in level 2 we have 1 ball, in level 3 we have 3 balls, and in level 4 we have 0 balls. We don't even need to draw the balls because we already know they are identical, all we need is the number of balls in each level. This is precisely the sort of description we're looking for. When I exchange any 2 balls like this, the number of balls in each level stays the same, so that this description also stays the same and we don't have any redundancy. Put another way, in this first case we're trying to characterize our system by asking the question, which ball is in which level? Because the balls are identical, this leads to a highly redundant description as exemplified by these 2 permutations of numbered balls. Instead, in the second case, we're trying to characterize our system by asking the question, how many balls are in each level? This avoids assigning labels to otherwise identical balls and provides a more compact description of the system. In quantum mechanics, the occupation number representation is analogous to this second situation. Rather than associating each particle with single particle state, and then constructing the symmetrized and antisymmetrized states with n factorial terms containing all possible permutations of particles, we describe states using the number of particles that are present in a given state, irrespective of which particle it is. In the rest of the video I will make these statements mathematically precise, but the basic idea is the one presented in this slide. Let's consider a system of n identical particles whose state space V is the tensor product over the n single particle state spaces V1 to Vn. Let U be a set of states forming a single particle basis, and I want to start with a refresher on some background needed to study the occupation number representation. If you want further details, you can find all the necessary videos linked in the description. You will remember from the video on tensor product spaces that we can construct a basis for the tensor product space V by calculating the tensor product of the basis states of the single particle spaces like this. As usual, we will omit the tensor product symbol moving forward and simplify our notation to this. This here is a basis for V, but we know from the video on the symmetrization postulate that the states describing a system of n identical particles don't really live in V, but in one of two subspaces of V. If the particles are bosons, they are described by totally symmetric states such that any permutation P alpha doesn't change the state, and these psi plus totally symmetric states span the subspace V plus. If the particles are fermions, they are described by totally antisymmetric states such that under any permutation P alpha, we get eta alpha psi minus state in the subspace V minus. In this final expression, eta alpha is +1 for even permutations and -1 for odd permutations, which remember means that exchanging pairs of particles an even number of times gives back the same state, and exchanging pairs of particles an odd number of times gives back the negative of the initial state. We also know that to obtain a state in V+, all we have to do is to act with the symmetrizer S+ up here on an arbitrary state in V, and similarly to obtain a state in V-, we act with the antisymmetrizer S-. All this means that if we want to describe an n-particle system of identical particles, we don't really want a basis in V, like we have here. What we want are the basis states in V+ and V-. So how do we build these basis states? As you may guess, they are simply obtained by applying the symmetrizer and antisymmetrizer to the basis states of V. Let's see how this works for V+. Start with an arbitrary state psi in V. Acting with the symmetrizer on psi, we obtain a state in V+. As psi is a state in V, then we can write it in the basis of V like this. And remember from the video on representations that the C coefficients are the representation of the state psi in the U basis. We can then build the state in V+ by acting with the symmetrizer on both sides of this expression, and we obtain S plus psi on the left, and S plus acting on the sum on the right. The symmetrizer is a linear operator, so we can move it inside the summation, and we get this long expression. So what does this mean? A state in V+ can be expanded in terms of basis states that are given by the action of the symmetrizer on the basis states of V. This means that as expected, when we symmetrize the V basis, we obtain a basis for V+. We can of course make an analogous argument to find that when we antisymmetrize the V basis, we get a basis for V-. As we just found, these symmetrized and antisymmetrized basis states form bases for V+ and V-. But as you may suspect, there is a lot of redundancy in these basis states. The full state space V is spanned by the tensor products of n single particle states. But V+ and V- are non-complementary subspaces of V, so their dimension is smaller than that of V. If we simply apply the symmetrizer or antisymmetrizer on every single basis state of V, then we will get as many basis kets as the dimension of V, which is many more basis kets than the dimensions of either V+ or V-. This means that this set contains repeated states, and we would ideally want to build a new basis for V+ and V- that doesn't contain repeated basis states. Before we can remove the repeated states, we first need to figure out which states are repeated. Given that we're dealing with systems of identical particles, we can already suspect that the states that will be repeated will correspond to different permutations of a given state. To confirm this, consider a basis state in V. Then apply an arbitrary permutation P alpha to obtain another basis state in V. From them we can build two basis states in V+. All we have to do is to apply the symmetrizer, and the first one gives this, while the second one gives this. Looking at this relation up here that we derived in the video on symmetric and antisymmetric states, we see that S plus P alpha is simply S+, so we obtain this. As expected, this state and this state are the same state in V+. This means that these two distinct basis states in V give the same basis state in V+. We can of course make a similar argument about V-, and we reach the same conclusion up to a minus sign in the definition of the basis states. Put another way, any permutation of a basis state in V gives the same basis state in V+ or V-. This This is the origin of the redundancy that we have in the bases for V plus and V minus when we build them by symmetrizing or antisymmetrizing a basis of V. But this makes perfect sense. Permutations of identical particles don't change the physics, so any permutation of a basis state in V plus or V minus should give the same basis state. So we have just found that if we consider any permutation P alpha of a basis state of V, then the basis states in V plus or V minus that we obtain by applying the symmetrizer or antisymmetrizer are repeated. This means that the representation provided by this basis is not ideal for studying systems of identical particles because there is a lot of redundancy, and it motivates us to introduce a new representation called the occupation number representation. So what do we want for this new representation? Because we're dealing with identical particles, any permutation of a basis state in V gives the same basis state in V plus or V minus. Therefore, we're looking for some quantity that is the same in any permutation of a basis state. Consider a single particle basis U and spell it out as U1, U2, and so on. To build the basis set of V, we need to take a tensor product over n single particle states as usual, but now I will build a very specific tensor product basis state in which I will first write out all the particles in single particle state U1, and I imagine there are n1 such particles. Then I will add all the particles in single particle state U2, of which there are n2, and so on. We call the number of times that an individual state appears its occupation number, and this means that the occupation number of U1 is n1, the occupation number of U2 is n2, and in general the occupation number of state UK is nk. Put another way, out of the total n particles, the occupation number nk tells us how many of those are in state UK. What we're going to do is to associate this list of occupation numbers with this particular basis state. Next, let's consider a permutation P alpha of this state we just wrote. The question now is, what are the occupation numbers of this new state? All the permutation does is to reorder the terms, but it doesn't add or remove any single particle states. So that state U1 still appears n1 times, state U2 still appears n2 times, and so on. This means that we can associate the exact same list of numbers with any permutation of a basis state of V. But this is it. We were looking for a quantity that is the same for any permutation of a basis state of V, and we just found that these lists of occupation numbers are one such quantity. So what will happen when we apply the symmetrizer or antisymmetrizer to these two states? The symmetrizer and antisymmetrizer are simply sums of permutation operators, so they will move around the states, but will not add or subtract any states. So after projecting onto V plus or V minus, we will still have the same list of occupation numbers for the resulting states. This means that we can characterize all permutations of a state by their occupation numbers. As these permutations are responsible for the repeated states we found in the bases of V plus and V minus, this means that we can directly use occupation numbers to uniquely label the basis states of the symmetric and antisymmetric subspaces, removing all redundancy we originally had. This leads to the definition of the occupation number representation. We write the state n1, n2, and so on as the symmetrized or antisymmetrized state of a corresponding basis state in V. Here I picked the ordered state for convenience, but from our discussion we can pick any permutation P alpha we want of this state, and it will lead to exactly the same definition of the occupation number representation. This all makes perfect sense because we're dealing with identical particles, so it shouldn't matter which permutation of the particles we use. There is a final detail in the definition of the occupation number representation. We will want to work with normalized states, so we will write a normalization constant in front here, a plus minus. A few points before we move on. First, it immediately follows that the total number of particles is equal to the sum over all nk. Second, it could be that there are no particles in a particular state, so that the occupation numbers may be 0. All we have left to discuss are the normalizations. Calculating them is tedious and not a very enlightening process, so I will not do it in this video. I have linked a reference in the description where you can find the details, or you can try it out yourself. For our purposes, all we need is the answer. If we start with bosons, then the occupation number representation of the state is given by the square root over these factorials, and then the symmetrizer acting on the tensor product basis state. The main question when looking at an occupation number state for a boson is how many particles occupy a given state. This is an example of a boson occupation number state, and what this means is that there are 2 particles in single particle state U1, so that n1 equals 2, then 0 particles in U2, so that n2 equals 0, 3 particles in U3, so n3 equals 3, 6 particles in U4 so that n4 equals 6, and so on. In general, we have an infinite number of single particle states U, but only n particles. This means that many of the occupation numbers will be 0, like in this example we had n2 equals 0, which meant that no particles were in the single particle state U2. To simplify notation, rather than writing the occupation number state like this, with n1, n2 and so on, what is typically done is to write out only the occupation numbers that are occupied, and it is then understood that the ones that are omitted have 0 occupation. So instead we will write ni, nj and so on, where ni is the first occupation number that is non-zero, nj the second one, and so on. Now let's turn to fermions. In this case, the occupation number state is given by the square root of n factorial of the antisymmetrizer applied to the basis state of V if all ui are different, and it is 0 if any two ui are equal. Remember that a totally antisymmetric state that we represent as a Slater determinant in the position representation vanishes if two particles are in the same state. This is reflected by this expression, and the main question for fermions becomes whether a state is occupied or not. The occupation numbers can only take values of 0 or 1, so this is an example of a fermionic state. And the corresponding occupations are n1 equals 1, n2 equals 0, n3 equals 0, n4 equals 1, and so on. Just like in the case of bosons, we can write the occupation number state like this, or we can also omit all the zeros and simply write down the occupied states like this. However, given that for fermions the occupation numbers of occupied states are all 1, then rather than writing the n's, we can directly write down the corresponding single particle state label. What this final expression is telling us is that the states that have exactly one fermion are ui, uj, and so on. Another critical point about fermions is that the order is important. This is because fermions are described by totally antisymmetric states which are defined like this. This eta alpha is the parity of the permutation, which you will remember from the video on permutations that it is the parity of the number of transpositions into which you can write out a permutation. What this means is that exchanging any two fermions introduces a minus sign, and the eta is telling us that exchanging pairs of fermions an odd number of times introduces an overall minus sign, and exchanging pairs of fermions an even number of times leaves the state unchanged. If we consider a fermionic state like this, and now exchange the two first occupied states like this, then this action is represented by a permutation that only exchanges the first two particles and leaves the rest invariant, which means it is a single transposition, so in this case eta is -1, so we need to introduce a minus sign in this equality. So what have we accomplished with the occupation number representation? Let's compare the two representations. In this formulation, we specify the single particle state that each particle occupies, and then after applying the symmetrizer or antisymmetrizer, we end up with n factorial terms in the calculations containing all possible permutations of the n particles in our system. The resulting expressions are therefore very long. For example, in the position representation in terms of wave functions, for bosons they take the form of a permanent, and for fermions the form of a Slater determinant. However, at the end of the calculation, many of these terms will cancel or be the same because the indistinguishability of identical quantum particles introduces a lot of redundancy in this description. This is equivalent to the case in which we labeled the balls in the example at the very beginning of the video, that also proved to have a lot of redundancy built in it. The occupation number representation resolves this problem. The relevant quantity when we have identical particles is not which particles, but instead how many particles occupy a state. This makes perfect sense. We have a system of identical particles which are indistinguishable, so assigning labels to them is meaningless. This is precisely what one would expect for a compact formulation of the physics of a system of identical particles, and this is why the occupation number representation is so powerful. The occupation number representation leads to a very powerful formalism to study systems of quantum identical particles, called second quantization. To learn more about second quantization, what you should check are the videos on Fock space and on the creation and annihilation operators that allow us to explore that Fock space. So why would you want to learn more about second quantization? It is the tool that allows us to study quantum systems in which the number of particles isn't fixed. For example, in relativistic quantum mechanics, so-called quantum field theory, or in quantum statistical mechanics. If you like the video or would like to send me suggestions for future videos, please subscribe.